Our group topic is formal verification of security critical hardware-firmware interactions in commercial system on chips. The presentation would have four parts. The first part is basic concepts and introduction, and the second part is method to ensure security, and the third part is primary task of bootcode, and the last part, methodology and result. Now we will talk about the basic concepts. The first concept is formal verification. It is an IC design verification method, and the main idea is to verify whether a design function is correct by using formal proofs. There are three formal verification methods. The first one is equivalence checking, and the second one is formal model checking, and the third one, serial prover. This paper focuses on model checking and emphasizes the utility of formal verification as a framework for regulation shown in the picture. First, we run model checking experiments on target system on chips and obtain some counterexamples. Then we do manual analysis to confirm whether those counterexamples are security vulnerabilities or not. If they are, then mitigate them. If they're not, which means all is good. And the second concept is hardware-firmware co-verification. It is the process of verifying embedded system software, which is firmware, runs correctly on the hardware design before the design is committed for fabrication. Now, here comes the question. Why we need hardware-firmware co-verification technicals? The first reason is that the manual review process, which is particularly important for security analysis of system on chips, has its own challenges. It's hard to scalable or repeatable and tends to be tedious and error-prone while dealing with hardware-firmware interactions. Specifically, hardware-firmware semantic differences, concurrency, and asynchronous nature of transactions make manual co-verification extremely challenging. Even it is true that automated verification tools could have aided manual review of hardware-firmware interactions. There is another problem, and that's the second reason. There are no such automated verification tools focused on hardware-firmware interactions. So, in this paper, we are presenting an effective methodology for formal co-verification of security-specific hardware-firmware interactions.
In part 2, I will introduce the hardware-firmware interactions in bootloaders. The bootloaders play a critical role in security of commercial SoCs. The reason why we choose bootloaders is that they can guarantee the SoCs will eventually run an authenticated operating system. The bootloader of boot RAM is actually the process of hardware-firmware interactions. In this process, we booted the hardware and verified the software. During the interactions, the SoC first powered on, and then we run the boot code, which is stored in the boot ROM. The SoC bootloaders contain a chain of loaders, with each one will verify the integrity and authenticity of the next one. This will create a chain of trust, which stems from an immutable root of trust. In our case, this trust root is boot RAM. After verifying the bootloaders, the SoC will run. The functions of bootloaders are they can limit the impact of malicious code and protect the register's assets. The key point in auto-checking is to guarantee the security of boot ROM. In this paper, we choose the model checking method to ensure its security. That's because the model checking can find banning corner case bugs, which are hard to find manually. This makes the model checking suitable for bug hunting in security critical modules such as boot ROMs. These modules may not be able to be repaired unfailed. If such vulnerabilities are found post-production, they will bring challenges to chip manufacturers, so we'd rather sacrifice scalability for high security.
I will introduce the primary text of the bootcode in three parts. The first part is configuration register locking. So the configuration registers set by the boot ROM are used in several critical hardware security flows. They can be used to stock keys, to temperature sensor configurations, and so on. So the boot ROM locks these registers after writing the configuration value and before control is transferred to untrust the firmware. And the logs provide the benefit of protection against the modification of a set by untrust agent. And the property of the locking is that guarantee that the respective locking function are always called in every security boot flow. For the second part is control transfer to project-based learning. I will call it PBL in the rest of the lecture. And after signature of PBL image are verified, whether control will be transferred to a PBL image copied from local memory or download from I/O interface depends on various boot configurations. So the boot ROM make decision depends on tens of such parameters. It will easily to make mistakes. So it's important to formally verify that the implement matches designer's intent. The property of this one is the decision tree of the boot ROM must implement the bootloader selection logic correctly. So for the last part is the text boot mode. So to facilitate debug of the boot process, Curtin SoC introduced a text boot mode. This allows a privileged user to run text code of their choice to boot the system. The property of this one is if execution of the user supplied the text code ends before the watchdog time expires, options of the system must halt.
As we talked in part 2, we use model check to ensure the security of boot ROM. There are two ways can be used for modeling in hardware-firmware interaction. The first is abstracting hardware to software. The second is abstracting firmware to hardware. In this paper, we use the first method. Because capturing hardware-firmware interaction and abstracting them into hardware model can be too detailed for commercial system on chips. In the test case in this paper, the firmware model is written in C language, and the hardware behaviors are abstracted to C subroutines. The high-level security properties are broken down into source-level assertions, and they are compiled into intermediate representation by LLVM. And last, we analyze this model by the model checker SMAC. As for the check results, a bug of test boot mode is found by model checker. That is, it's possible to continue normal execution after user test execution already completed. As for other two properties, SMAC hits these properties after a period of time, but we found that they are just designer's intents. This methodology has traditional scalability constraints, but it's time-saving, taking only 1 day of work by one engineer and very high efficiency. In the example case, model checking only cost 400 seconds in total. In conclusion, in this paper, we describe specific hardware-firmware interaction pattern of commercial system on chips and identify specific challenge in firmware verification and demonstrate property-specific abstraction is a viable methodology. We believe that firmware verification has strong potential in verifying interesting security properties for hardware-firmware interaction in commercial system on chips. Thanks for listening.